On this page, we will examine the GeoGebra worksheet that I've created to visualize Euler's method for estimating the solution for initial value problem for the differential equation derivative is equal to some function of x and y with an initial value given by the value of f at some a equals c, which we'll call y0. Euler's method for estimating the solution to the initial value problem is to estimate the value of f of b given f of a is equal to c in n steps. To do this, Euler's method will cut the interval from a to b into n equals segments of length dx or delta x, being b minus a divided by n, and that x sub k is used to denote the value of a plus k times the change dx. Yk plus 1 then is determined by the previous yk with a differential determined by that yk, so that differential is given by the derivative p of xk yk times the differential in x dx, and that's added to yk to give us yk plus 1. If you do this n times, the value of y capital N will be approximately the value of f of b. And that approximation is based on the fact that at each little step we're approximating the value of the function at that next x using the differential. So when the dx is small and the n is large, the approximation will be a better approximation, assuming that the function is continuous. The function p of x, y is a continuous function of both x and y. In the worksheet I've created, the left-hand section has a spreadsheet built in GeoGebra that outlines and computes the Euler's methods for each x starting at 0, and in this case going till 1 in 4 steps. In the first step, we find the value given to us as the value at 0 is 2. From that we compute the derivative and then the differential based on the derivative being, in this case, 2x minus y. So twice the first coordinate minus the second coordinate gives us the derivative. So that gives us this derivative. We multiply by the change in x, which is 1/4 here, and we get minus 1/2, and that is added to 2 to give us the first change in y, which is then added to 2 to give us 1.5 as the estimated value at 1/4. This continues along each row, giving us the next value, each row giving us the next value, until we arrive at the estimate of 1 at 1.2656. So we've estimated the value of our function at 1 by 4 steps, each one using the differential. That is visualized in the mapping diagram by having the input values of 0, 1/4, 1/2, 3/4, and 1, and arrows drawn to the appropriate y value determined by Euler's method, starting at 2, then down to 1.5, then down to 1.25, then down to 1.1875, and then back up to 1.2656. So each arrow is determined by the pair in the table given by the computations from Euler's method. This is also visualized here in the xy Cartesian plane by the points being at 0, 2, then 1/4, 1.5, and so on, arriving at the final ordered pair 1, 1.2656, and the lines drawn between these points actually indicate our line segments indicating the differential for that interval, and these are actually the differential estimates given the current value as to what the differential estimate would be for the next value. To make that a little more clear, let's show the slope field that goes with this differential equation. and one can see how this curve, which is a piecewise linear curve that estimates the actual curve for the solution of the differential equation, how that fits pretty well into the slope field drawn, again, using GeoGebra's built-in slope field feature. We can also see in this worksheet the effect of changing the number n to give a more accurate estimate. So changing n to 5, the step size changes from 1/4 to 1/5, and we can change the value of n further to 6, 7. We change it to a step size of 1/10, determined by n equals 10, and we see a more accurate estimate given for the value of f at 1, as well as a more accurate curve in the Cartesian graph to visualize the solution as the graph of a function, as opposed to visualizing the solution here as a mapping diagram, estimating the mapping diagram for the actual function. We can change the value of n higher and get more accurate results. With this n, we can go all the way up to n equals 100, and that gives us a fairly precise estimate for the solution at 1.4641. And you see that the mapping diagram now is pretty well complete with arrows so that you can see no gaps in the arrows. And on the Cartesian graph, we see a curve visualized by 100 points, which is so dense that we can not discern the line segments between the points in this scale. To summarize, we've used Euler's method to estimate the solution to the differential equation. The derivative is 2x minus y, with the initial value of f at 0 being 2, and we've used that to estimate the value of the function at 1 with n equals 4 as our starting choice, giving us 4 steps in Euler's method to estimate the value of the function at 1.